Welcome to the video lecture on course code U18Pcit601, course name Grid and Cloud Computing. And I am Dr.B. Dhanalakshmi, Professor, Department of Information Technology, Bharat Institute of Higher Education and Research. And today we are going to see Unit 1, topic Grid Computing. So now we will see first what is grid computing. So grid computing is a form of distributed computing, whereas a super and a virtual computer here is composed of a cluster of networked loosely coupled computers, which performs very large tasks. And grid computing, according to Foster and Kesselman in 1999, defined that it is a growing technology that facilitates the executions of large-scale resources and intensive applications on a geographically distributed computing resources. And grid computing also facilitates flexible, secure, coordinated large-scale resources in a distributed environment which share dynamic collection of individuals, institutions, and resources. And grid computing also enable communities, that is virtual organizations, to share geographically the distributed resources as they pursue the common goals. And now we will see the criteria for a grid. So the first criteria is it coordinates the resources that are not subject to centralized control. And grid uses standard, open, general purpose protocols and interfaces. And grid delivers non-trivial qualities of services. And now we will see the benefits of grid. So grid exploit underutilized resources. So the resources will not be wasted. Here, the resource management is very well planned in grid computing. And grid computing also involved in resource load balancing. Equally, it distributes the resources in a network. And grid computing virtualize the resources across the enterprise network. And we can create data grids and compute grids for different real-time problems. And this grid enable collaboration for virtual organizations to share the resources. And now we will see the grid applications. And first in domain, we'll see about data and computationally intensive applications. So this technology has been applied to computationally intensive scientific, mathematical and academic problems in real time, like drug discovery, economic forecasting, seismic analysis, back office data processing, supporting e-commerce applications. A chemist may utilize hundreds of processors to screen thousands of compounds per hour. And teams of engineers worldwide pool the resources to analyze the terabytes, that is large amount of data which are in structured form. So, and even meteorologists seek to visualize and analyze petabytes of climate data with enormous computational demands. So every second, the weather is recorded at various parts of the world. So all these are possible due to grid application. And next domain is regarding resource sharing. So computers, storage sensors and networks, we have this resource sharing. So sharing always conditional where issues of trust, policy, negotiation, payment can be encountered. So the resource sharing includes the sharing of processing units, memory, and so on. And next domain, we will see about coordinated problem solving. So here we use this grid computing in distributed data analysis, computation, and collaboration of different domains in an enterprise network. And now we will see about grid topologies. So the first topology is intra-grid. So intra-grid is a local grid within an organization. And here the trust is based on the personal contracts. And next topology is extra-grid, where the resources of a consortium of organizations are involved. An extra grid is connected through a virtual private network. And here the trust is based on business to business contracts. And at last, inter-grid topology, where the global sharing of resources are done through the internet. And here the trust is built based on the certification. And now we will see about computational grid. So here the computational grid can be defined as a hardware and software infrastructure that provides dependable, consistent, pervasive and inexpensive access to high-end computational capabilities. And the grid blueprint for a new computing infrastructure defined by Kesselman and Foster. An example, Science Grid, which belongs to US Department of Energy, is a computational grid. And now we will see about data grid. So a data grid is a grid computing system that deals with data. The controlled sharing and management of large amounts of distributed data. And data grid is the storage component of a grid environment. And also data grid is involved in scientific and engineering applications which require access to large amount of data in a distributed environment. And data grid also provides seamless access to the local or remote data which are required to complete compute intensive calculations. For example, Biomedical Informatics Research Network and the Southern California Earthquake Center implements this data grid in their centers. And now we will see the different methods of grid computing. The first method is about distributed supercomputing, and the second method is about high throughput computing, which enhance the performance of the grid. And third is on-demand computing, where based on the demand of the resources, the data is distributed among the different grid. And next is data intensive computing, which focus on the data centric. And next is collaborative computing, where the distributed resources are involved. And at last, logistical networking. And now we will see about distributed supercomputing. So distributed supercomputing combines multiple high capacity resources on a computational grid into a single virtual distributed supercomputer. So here it tackles the problems which cannot be solved on a single system. And next we will see about high throughput computing. So high throughput computing uses the grid to schedule large numbers of loosely coupled or independent tasks. And this fixes the goal of putting unused processor cycles to work, thus enhancing the performance of the grid. And next computing is collaborative computing, which is concerned mainly with enabling and enhancing human-to-human interactions. And here the applications are often structured in terms of a virtual shared space. And next we will see about data-intensive computing. Here, the focus is on synthesizing new information from data that is maintained in the geographically distributed repositories, digital libraries, and even databases. So mainly here in data intensive computing, the focus is on the information that is obtained in an enterprise network. And this is particularly useful for distributed data mining applications. And now we will see about logistical networking. So logistical networks focus on exposing storage resources inside networks by optimizing the global scheduling of the data transport and the data storage. So this logistical network contrasts with the traditional networking method, which does not explicitly model the storage resources in the network. And this model is a high-level service for grid applications. The name logistical here because of the analogy it bears with the systems of warehouses, depots, and distribution channels. So this networking mainly focus on the storage resource, how to distribute the storage resources and how to transport and how to schedule the transport and how to schedule the stored data among the distributed network. And now we will see the difference between P2P computing versus grid computing. So here P2P computing, peer-to-peer computing is a traditional method which, which is which has more disadvantages. Now it has been overcome in the grid computing. And here grid computing mainly focus on the communities in a distributed network. So, but peer-to-peer computing will differ in the target communities. So, it will have the limited networks in the peer-to-peer computing. And grid system deals with more complex, more powerful, more diverse and highly interconnected set of resources than peer-to-peer networks. And now we will see the architectural diagram for the grid environment. And here the main component is grid information service, where we store the details of the different grid resources used in the network. So grid resources can be a cluster, a personal computers, supercomputers, database, instruments, sensors, etc. So which are available from the global grid and thus execute the user jobs. So the information about the grid resources are stored in the form of metadata in the grid information service. So this grid information service system collects the details of the available grid resources and passes the information to the resource broker. And the resource broker distribute the jobs, the user jobs in an application to the grid resources based on users' quality of service requirements and details of available grid resources for further executions. So the quality of service attributes enhance the performance of the grid. And this resource broker is responsible to allocate the jobs to the appropriate grid resources based on the requirement. And the availability of the grid resources will decide the allocation of the appropriate grid to the user. And, and third component we are going to see is the user component, who is going to interact with the grid application and going to analyze the computational result. A user sends computation or data intensive application to global grids in order to speed up the execution of the application. So here, once the jobs are processed, they are delivered from the grid resources via the grid application to the end users. And the end users, once receiving the result from the grid resources, can analyze on it and can bring a conclusion or can decide, and which helps him for decision making. So overall, the main grid resources details are stored in grid information service, and grid information service is mainly responsible for collecting the details of the available grid resources and thus passing the information to the resource broker. And this resource broker is mainly responsible to distribute the jobs in an application to the appropriate grid resources based on the user's quality of service requirements, QoS requirements, and also the availability of the grid resources. And the user will interact through the grid application and thus utilizing the grid resources, and once the processing of jobs in the grid resources end is over, it will return the result, the computed result, to the user. And the user will analyze the computation or the data intensive application to global grids in order to speed up the execution of the application. And now we will see about grid middleware. So grids are typically managed by gridware, which is a special type of middleware that enable sharing and manage grid components. And this is based on the requirements of the users and also the attributes or features of the resources shared. So the attributes of the resources can be capacity, performance, and so on. The software that connects other software components or applications which provide the following functions. And the first main function is to run the applications on suitable available resources, that is brokering and scheduling. And here the grid middleware provide uniform high-level access to the resources shared. And here the semantic interfaces will be easily interacting with the user and the grid resources. And here in grid middleware, we have web services, service-oriented architectures, and inter-domain issues of security and policies also are addressed. And this grid middleware has federated identities that can be implemented here. And next we will see about middleware available, that is Globus in Chicago University, Condor and Wisconsin University, which has high throughput computing, and Legion in Virginia University, which has virtual workspaces and collaborative computing, and then IBP, which has Internet Backbone, Tennessee University, that is logistical networking. And next you have NetSolve, which solves the scientific problems in heterogeneous environment, that is high throughput and data intensive units. And now we are going to see the two key grid computing groups in real time. So the first group is Globus Alliance, which is composed of people from Argonne National Labs, University of Chicago, University of South California, and Information Sciences Institute, and University of Edinburgh, and others. And we have OGCA-I standards initially proposed by the Globus group. And the second grid computing group we have is Global Grid Forum, where the heavy involvement of the academic groups and even the industry group is also present. So here the IBM Grid Computing, then HP, United Devices, Oracle, UK eScience program, US DOE, US NSF, Indiana University, and many others have belonged to this group of Global Grid Forum. And this process meets 3 times annually and solicit involvement for industry, research groups, and academics. Here, the collaboration of the academics and the industry is more highlighted in the groups which belong to this grid computing environment. And here are some of the major grid projects. The first project name is Eurogrid, that is Grid Interoperability GRIP. So here the URL or sponsor is European Union, and which focus mainly on creating tech for remote access to supercomputer resources and simulation codes. And here it integrates with the Globus toolkit. And the second grid computing project is Fusion Collaboratory, which belongs to the URL or sponsor DOE of Science, and which focus on creating a national computational collaboratory for fusion research. And the third project is Globus project, and here DARPA, DOE, NSF, NASA, Microsoft are the sponsors. And this Globus project focus mainly on grid technology related research, development and support of Globus toolkit, and application and deployment. And next is Grid Lab project, which is supported by European Union and which focus on grid technologies and applications. And next project is Grid PP, which is sponsored by UK eScience, and this focus on the operational grid within UK for particle physics research. And the last project mentioned here is Grid Research Integration and Support Center, which is sponsored by NSF, and this focus on integration, deployment, and support of the NSF middleware infrastructure for research and education. And now we will see the grid architecture, that is the RGlass model. This RGlass model focuses on architecture issues that propose the set of core services as basic infrastructure. And this architecture used to construct high-level, domain-specific solutions which are in diverse areas. And this is used for design principles and which keep participation cost low, and this also enable local control and the support for adaptation. And here the IPHOR glass model is also given here, where we can see the diverse global services are involved, and here the core services are also present, and the local OS which is going to interact with the user is also involved. And now we will see the layered grid architecture by analogy to internet architecture. And here it coordinates multiple resources, that is ubiquitous infrastructure services, that is application specific distributed services are handled here. And another layer sharing single resources, negotiating access, and which also control the use. And the next is talking to things, that is communication, which involves the internet protocols and security. And here even the control of the local things, that is access to and control of the resources, are also monitored. And here in the diagram, we can see the internet protocol architecture, which is used in layered grid concept. So where we can see the application which interacts with the collective resources, and connectivity related, communication related. So concepts are also related to the application. Okay. And we have transport and the internet protocols used here in the architecture. And now we'll see the example that is data grid architecture irrespective of the different layers. So application layer, here the discipline specific data grid applications are involved. And next layer, collective application, that is coherency control, where the replica selection, task management, virtual data catalog, virtual data code catalog, all are focused. And the third layer, generic, which is collective, that is replica catalog, replica management, co-allocation, certificate authorities, then metadata catalogs are all focused. And next layer is resource, where the access to the data resources, access to computers, access to network, performance data are all focused. And next layer is connect layer, which is mainly for communication, that is message passing, service discovery, authentication, authorization, and delegation. And the last layer is fabric, which involves the storage systems, clusters, networks, and network cache areas. And here are listed some of the simulation tools. The first tool is GridSim, which is for job scheduling. Then SimGrid, which is single client multi-service scheduling. And Bricks, which is for scheduling. GangSim, OptoSim for data grid simulations. And G3S, which is for grid security services simulator, mainly focused on the security services. And simulation tool is mainly, we are going to now see about the GridSim, which is a Java-based toolkit for modeling and simulation of distributed resource management and scheduling for conventional grid environment. GridSim is based on SimJava, a general purpose discrete event simulation package implemented in Java. All components in GridSim communicate with each other through the message passing operations defined by SimJava. And next, we will see the salient features of the GridSim. This allows the modeling of heterogeneous types of resources. And distributed resources are also focused here in GridSim 2. And resources can be modeled operating under space or time shared mode. And resource capability can be defined in the form of millions instructions per second, that is benchmark data. And resources can be located in any time zone. Weekends and holidays can even be mapped depending on the resources location time, that is local time in the distributed location to model non-grid workload. So resources can be booked for advanced reservation of the, like when we share the resources in a distributed network, we need an advanced reservation of the resources that can be booked. So applications with different parallel application models can be simulated. And here in GridSim, we can integrate and synchronize different applications and different operating issues here in the GridSim 2. And here is the Web 2.0 clouds and Internet of Things all involved in this architectural diagram. So first in the topmost here is the HTC system disparate nodes and the homogeneous nodes HPC systems are given. So the high performance computing, so here handle the data in clusters or MPPs. So which has a centralized control. And the traditional network is given on the left side, which is P2P network where the file sharing is done in the distributed control. So this computational and data grids involves the service-oriented architecture, that is Web 2.0 services, and virtualization, that is Internet clouds, and RFID and sensors, that is Internet of Things, are also involved in the computational and data grids. So here, the high performance computing and the high throughput computing are involved in the Web 2.2 network. And this MPP or clusters can be massively parallel processors which has a centralized control over the computational and data grids. So thank you, students. Thank you for listening.